Hello and welcome to iitiansgateclasses once again. So in the previous lecture, we have seen some of the recursive relation methods, and using these methods, we can calculate time complexity also. So you have seen one example of recursive tree method. Actually, solving of these recursive or recurrence relation method covered in mathematics. Okay, this is the part of mathematics and no algorithm, but still I will give you some basic idea about it. Okay, so like how are we going to cover this? Some examples. I will start from very basic and I will give you some intermediate and one or two complex examples also to solve this. So you have already seen the recursive tree method, using which you can basically build a tree for an algorithm and you can calculate the time complexity. Okay. Similarly, now today we will see the master method algorithm as well as substitution method. So starting from master method, actually this is this recursive relation is actually called recurrence relation, right? Because if you see the standard, if you see this standard template here, right? This standard template here, we are basically doing a recursive relation. It's recursive. Like right now, it's a function. The t is function, and we are passing n. Then in the same function, we are passing n by 2 and multiplying that with 2. So it's recurrence relation. It's not recursive relation method. It's called recurrence relation actually. You can call it recursive method also, but the actual name is recurrence relation. Okay. So I will be today I will be doing master method also, but for this recurrence relation, RECURRENCE, recurrence relation. Okay, so let's start with master method. Then I will also solving substitution method example and limitations of master method also. So if the given recurrence relation is in form of this thing, wait a second. Okay, so if the recurrence relation format is in form of this Tn equal to A T n by B plus Fn. So Fn is some function, right? It's some function. So I'll be telling you the format of the Fn function also, as well as the constraint for A and B. So if this is the format of recurrence relation, see the building of recurrence relation we will cover later on when we go to the algorithm part, where we will be solving some of these algorithms. So we will be also building recurrence relation there, and using those recurrence relation, you can calculate time complexity, and otherwise using some common understanding also, like how many iteration it's taking, how much time it takes to consume the input and produce the output. Okay, so using such things also you can calculate. Using such things also you can calculate time complexity. But the ideal way is actually build the recurrence relation, and through which you can calculate time complexity. The building of recurrence relation I will tell later on. So once you have the recurrence relation in GATE examination, you will also see recurrence relation or these kind of functions where you are given with some function like this in this format, where A and B are basically constants. Okay, and the value A should be greater than 1, B should be greater than 1, and the function f should be positive, asymptotically positive. I have told you asymptotic notations, right? So it should be asymptotically positive. Asymptotically positive. Okay. So once you are given in the given the recurrence relation in this format where these constants are satisfied, then only I'll be solving some example also. Okay. So you can solve and calculate the time complexity. So, or you can say that the time it will take to solve this recurrence relation. Okay. So right now there are few cases here. So we have case one here, case one, which says that if this Fn is equal to order of n log base B A, this is the B, right? This B, base B A minus some value, okay, for some epsilon greater than 0. This is some value epsilon, okay. If this is the format, right, then Tn is equal to theta of n log BA, right? Oh, what I'm saying here is that Fn should be lesser than this, right? If I will be solving some example also, don't worry about it for all the cases. But right now, remember this, all we are saying that all and over Fn should be greater than n and log base B and A. The epsilon part is like, if we reduce the value to a bit also, it should still be the greater than Fn. It should still greater than Fn. Then Tn is this, theta of n log B base B and A. Okay, n to the power log base B and A. The case 2 is case 2. It's just opposite of this case. If Fn equal to, or you can say equal to omega of n log BA plus sigma, where sigma is greater than 0. Okay. So what we are saying here is that all and over this function n to the power log base BA is lesser than Fn for every constant of B and A. If it's lesser, then we will say that Tn is equal to theta of Fn. Right? Then we will consider Fn as a upper case limit or the value for Tn or equal. Right? Theta means equal. Big O means upper limit. Omega means lower limit. So it is not upper limit, sorry, it's theta. Right? The T value of Tn is equal to almost around theta of Fn. Right? So let's consider the case 3. Case 3 is most important case. If some question are asked on master theorem, mostly it lies in case 3. Case 3. Right. Here it says that if Fn is equal to, or you can say that Fn is equal to theta of n log BA, log base B and A, n to the power log base BA, then in that case, Tn is actually equal to theta of n log base BA, and we are multiplying the whole term, this whole term with log n. Okay. So this is the solution. So now let's solve some example to get more like better understanding of this. Let's start something like this. Okay. So here I'm solving this case 1. You can say case 1 example. So you can go back and check the case 1 where Fn is actually equal to order of n log base BA, where we can say that Fn is smaller than n log base BA. Okay. So in that case, answer is this one, n log base BA. Okay. So let's start with this example where we are saying that Tn is actually equal to 9T n by 3 plus n. Okay. So let's check what is A, what is B, and what is Fn. So right now Fn is actually n. If you see, this is Fn. Fn is actually n. Okay. A is actually 9, B is 3 here. Okay, so what is the value of n log base B A? What is it? N log base B, log base 3, B is 3, right? 9. And if you solve this, the value of this is actually 2, right? Log base 3, 3 to the power 2, okay, and you can put 2 here, and this whole term log 3 is 1, so it's n square. Okay, so now if you compare Fn with this thing, n log base B, this term is greater, right? So we can say that Tn is equal to n square. This term is n square, right? Here Fn is n, and this term is n square. So Tn is equal to n square, the case 1 part, right? N is equal to order of n square, right? Here if you see, and this is the first case. Log base B A minus epsilon. Epsilon is some small value, right? Some small constant value. So if this is the case, then Tn is equal to theta of, so it's theta of n square, right? Not n square, theta of n square, theta of n log base B A. This is the first case. And if you see that n log base B A here is n square and Fn is n, then in that case, answer is Tn equal to theta of n square. So this is the first case. Let's move to the second case. Case 2. Case 2 example, right? So if you see the example of case 2, it's Tn equal to 2Tn by 2 plus n square. This is n, okay? 2Tn by 2 plus n square. This is Tn value. Tn equal to 2Tn by 2 plus n square, right? So let's see, what is Fn? Fn equal to n square. What is A? A is equal to 2. What is B? B is equal to 2. So now let's calculate n log base B and A. What is it? It's equal to n log base B. What is B? Sorry, it's equal, multiple. It log base B, what is B? 2. And what is A? 2. And value of log, if the base and value is same, it's equal to 1. So it's equal to n actually. So if you see here, Fn is n square, n log base B and A is n. If you add any kind of constant here, any constant or epsilon is constant. Okay, any constant value, still Fn will be greater, right? So we can say that Fn equal to sigma of n log base B A plus epsilon, which is n square is equal to sigma of, if you remember asymptotic notation, we can denote it like n to the power 1 plus some constant value, which is actually equal to sigma of n, right? So n square. If this is the case, then we can say that Tn equal to theta of n square, right? This is the answer. Now let's move to the most important case, which is case number 3 example. Case number 3 example. If we say that there is an example, Tn equal to 27 Tn by 3 plus n cube. Now, if you remember the case 3, what is case 3? It says that if these two functions are equivalent, then the answer is actually n log base B A log n, or you can say Fn log n also. It's the same thing, Fn log n. Okay, is the same thing, theta or Fn log n. These two are same because these two values are same. Okay, now let's calculate n log B A. What is the value of B? 3. What is the value of A? 27, which is n log base 3, 27. 3 to the power 3. 27 is 3 to the power 3, which is equal to n cube. Okay. If you put 3 here and log base 3 and 3 will be 1, right? So it's n cube. So now if you see this term and Fn here, Fn is n cube, right? These two terms are equal. So the answer is actually Tn n cube log n, theta of n cube log n. This is n, right? Theta of n cube log n. This is the most important case. Now let's see one more example where we will see that this master theorem is not applicable to all the terms, right? And we will see the reason also. For example, if you want to solve this thing, Tn equal to 8t n by 2 plus n cube divided by log n, right? Now if you calculate this, n to the power log ba, which will be n to the power log base 2, 8, which will be equal to 3n cube, right? N cube. Now if you see here, Fn equal to n cube divided by log n. So n cube is obviously greater than n cube divided by log n, but you can't say that answer is n cube, because here this function is not polynomial. It's logarithmic. It's logarithmic because log is involved in it. So the constraint is that Fn should be, remember this, should be polynomial. And the other term should be in form of this. Right? It should be this one plus Fn. The format should be like this, and Fn should be polynomial. Then only we can use master theorem. Otherwise, we cannot use master theorem, and you may happens to be like writing wrong value in the examination. So remember this constraint that Fn should be polynomial. Okay, we are saying that Tn equal to A, T, n by B. So Fn should be polynomial only. Polynomial means in power of n. For example, like n square, n cube plus 5, something like that, right? And we have right to basically eliminate these constants. These constants, we can eliminate these constants, right? This constant we can eliminate. So whenever you are given with example like if Fn is equal to n cube plus n square, right? You have right to consider this as n cube only. Okay, you can consider it as n cube, and you can go ahead with the calculations. So you can reduce the given recurrence relation into master theorem recurrence relation. Master theorem recurrence relation means the format should be this one. So you can reduce the problem to this problem, but this Fn should be polynomial and the other term should be in this format only, right? So I already told you that you can write n cube plus some constant k as n cube. So this is also polynomial, right? With single term. So right now, if we are done with master theorem, let's move to some substitution method problem where master theorem is not applicable. Okay. So let's see Tn equal to Tn minus 1 plus n. So if you try to write this as Tn plus n, right? If you try to write like this, then what is the value of A? It's 1. What is the value of B? It's 1. And in the constraint list, we have seen that already. In the format, the A should be greater than equal to 1 and B should be greater than 1. Here, the value of B is basically 1. So master theorem is not applicable here. Okay, master theorem is not applicable. So we have to do some processing here. Right? So constraints are not satisfied, so we have to do some other method, which is substitution method. And we are given that this is the case. Plus, when n equal to 1, the answer is basically I think it's 1. Okay. If n is greater than 1, then the answer is this. So let's try to solve this. If we write Tn equal to Tn minus 1 plus n. Okay. Then replace this Tn minus 1. What is the value of Tn minus 1? Tn minus 1 is basically Tn minus 2 plus n minus 1, right? And n is already there. Why we have written this thing like this? If you look at the recurrence relation, it says that Tn is equal to Tn minus 1 plus n. So let's replace n with n minus 1. Let's replace n with n minus 1 here. It is n minus 1 equal to Tn minus 1 plus n minus 1, right? Which is Tn minus 1 equal to Tn minus 2 plus n minus 1, right? So we have replaced the Tn minus 1 here with this term. The same thing goes again, replace n with n minus 2. Okay, it will be Tn minus 3 plus n minus 2, and these two terms will remain same, plus n minus 1 plus n. If we keep on replacing like this, we will be getting terms like this, right? Until we go to n equal to 1. So let's iterate this thing n times. We iterate this thing n minus 1 times, not n time, n minus 1 times. So we have seen that Tn equal to Tn minus 3 plus n minus 2 plus n minus 1 plus n, right? So if we keep on iterating and try to replace n minus 3 with n minus 4, n minus 5, n minus 6 till n minus 1 times. Why n minus 1 times? Let me tell you that we are trying to reach the base condition here. Base condition is if value of n is equal to 1, the value of T1 is equal to 1. It's saying that if we replace n with 1, its value is 1. And in the case of greater than 1, the value is this. And we are not going below n equal to 1. Okay. So let's iterate this till n minus 1. Replace the value of n with n in the Tn, replace the value of n with n minus 1. So it will be Tn minus n minus 1, right? Each time we iterate, this value will increase by 1, right? So if we iterated n minus 1 times, the value will here be n minus 1, right? And we have gone to like this. So here, n minus 2 plus n minus 1 plus n. Okay. So if we have iterated this n minus 1 times, what happened in this in between this, right? In between these iterations. Here you have seen n minus 3, n minus 4, something like this, okay? And what is the last term before n minus 1? What was here? N minus 2, right? So value would here be, what was the value here? N minus 2, which is actually 2. Just before n minus 1. What happened in n minus 2th iteration? N minus 2th iteration. What happened at that iteration? Okay. So in the third iteration, you have seen that the value is n minus 2. So which is actually n minus 3 here and you write n minus 2 here, right? In the third iteration. Okay, so I think I'm confusing you guys. What I'm doing here is I'm simply iterating these values. So you have seen that we have reached till here very easily, right? So we will keep on putting the values. So once we put n minus 2th value here in n minus 2th iteration, the value outside it will be n minus 2, right? Because here, if you see, whatever value we put here, the same value will appear here, right? So in 0th iteration, it is nothing but n minus 0. In the first iteration, it is n minus 1. You have seen that. In first iteration, it's n minus 1. In the second iteration, it's n minus 2. Right? In the second iteration, it's n minus 2. So in n minus 2th iteration, it will be n minus 2, which is actually 2. Okay. So what happened in case of n minus 1? The iteration goes like this: t n minus 1 plus 2, 3, 4, 5. I'm going backward. N minus 2 plus n minus 1 plus n. Okay. And what is the value of t n minus 1? It is t1 equal to 1. So tn would be 1 plus 2 plus 3 plus 4 plus n minus 2, n minus 1 plus n, which is actually equal to n plus 2. Simple sum. Like simple arithmetic progression sum. N square plus n by 2, which is equal to order of n square. We are taking the maximum power order of n square, eliminating the constant, and this is order of n square, big O of n square. Tn equal to order of n square. I will be solving more example, but right now you have to understand this example that I am doing nothing but substituting the value of n with a smaller value, whichever is given. I am substituting the value of n with smaller value, whichever is given in the recurrence relation. Now it's given n minus 1, right? So let's see more examples, something like n by 2, okay, which we could have solved using this master theorem also. So you can guess the answer using master theorem, but right now let's go with if n equal to 1. You can guess the answer using master theorem, but I will try to solve the same example with substitution method. Okay, so this is the recurrence relation given to you. If you try to solve this, let's try to do the substitution. Initially, this is a step. Okay, so once you replace n with n by 2, what will happen? So we are calculating value for this one. Okay, this is sorted. We are calculating value for this one. Tn by 2. Once we replace n with n by 2, okay, so we are given that tn equal to tn by 2 plus n, right? This is given. Let's replace n with n by 2. Tn by 2 divided by 2, right? Plus n by 2. This will happen. We have replaced n with n by 2. So it's tn by 2 equal to tn by 2 square, right? It's n by 2 square plus n by 2. It's the same thing, right? Now, this is sorted, right? So let's replace n by this n with n by 2 again. In n by 2, let's replace n with n by 2 again. So it happens that tn by 2 square will be, so we are going to calculate value for this one, right? It will be here. Let's assume that this is the function, this is the initial function. We have replaced n with n by 2. We have reached to this step. Now we have also, we need to calculate value for this one also, right? We need to calculate value for this one also, right? So let's replace n with n by 2 square in this function, or in this function. Okay, let's replace n with n by 2 square in this function. This will be t n by 2 square, t n by 2 cube will appear here, okay? Plus n by 2 square. We have replaced n with n by 2 square here, and we will end up to this. Okay, now you know that t n by 2 is this function which is t n by 2 square plus n by 2. N was already present here. Now we are going to focus only on this one. What is the value of this thing, which is t n by 2 cube plus n by 2 square plus n by 2 plus n, right? We will keep on doing this until we reach to a certain value where this value is reduced to 1. This value is reduced to 1. Okay, we will iterate this till this value is reduced to 1. So how many times should we iterate this? Let's calculate that. Right now you know that Tn is equal to Tn by 2 cube plus n by 2 square plus n by 2 plus n, right? So we will keep on doing this step till this value reaches to the base condition. Base condition is n equal to 2, n equal to 1. Okay, so whenever we iterate this step, the power of 2 is increases by 1. Okay, the power of 2 is increases by 1, and here we have added one more value, right, which is far lesser, which is 1, like in denominator the power of in numerator in denominator the power of 2 is basically is 1 lesser compared to this one. So if I say that I repeated this value to kth step, okay, kth step, where this term n upon 2 raised to power k become 1. We are saying that it's become 1. So k says that these many times we have reiterated this step. Okay, so what is the value of k? N equal to 2 raised to power k. Let's take log both sides, log base 2. So k equal to log base 2 n. We need to iterate this step log n times, log base 2 n times, log n times. We need to iterate this step. Okay, so once we repeat this log n times, we will reach to this thing, T1 equal to plus n upon 2 raised to power k minus 1 plus n upon 2 raised to power k minus 2 plus n upon 2 raised to power 2 plus n upon 2 plus n. Okay, so what is the value of k and what is the value of t? T1 is 1. What is the value of k? It's log n, 2 raised to power log n minus 1 raised to power log n minus 2 plus n by 2 plus n. Okay, so this is the equation we need to solve now to get the answer. Okay, so let's take n common here. N is common. We will remain with this one. Log n minus 1, log n minus 2, 1 upon 2 plus 1 upon 2 raised to power 0. 1 is, we can write 1 as 1 upon 2 raised to power 0 also, right? Once we take n common from this term, if we take n common here and we put it outside, we can write it like 1 upon 2 raised to power log n minus 1 plus 1 upon 2 raised to power log n minus 2 till this, right? So this we need to solve now. If you look at this one, this is a GP only. Okay, so if you don't remember arithmetic geometric progression, let me write the answer for GP. Right. So if the value is, in case of GP, in case of GP, the sum can be written like this. Okay. The sum can be written like this. If we have terms like this, R plus R square plus R cube plus Rn, right? So here, if sum is Sn, the Sn can be written like this: 1 minus Rn upon 1 minus R, right? We can write it like this. Okay, if R is not equal to 1. So if you remember the form of GP, we can write it like this. Okay, so considering this here, let me write it again. Tn equal to 1 plus n, 1 upon 2 raised to power log n minus 1. Okay, so let me try to write it in reverse order. It's 1 upon 2 raised to power 0 plus 1 upon 2 raised to power 1 plus 1 upon 2 raised to power 2 log n minus 1 times. Okay, n minus 1 times. This is the log n time iteration, and this is log n minus 1 time. So this is the GP, and the answer here is 1 plus n upon. So what is the value of R? It's 1 by 2. It's 1 by 2, right? It's 1 by 2. So here the GP is with power 1 to n, right? 1 to n. And in our case, it's R to 0, 0, 1, 2, n minus 1, right? It's that many times. So here the value of n is not n, it's n minus 1. It's n minus 1. But the number of terms, if you count the number of terms with 0, 1, 2, and n, the number of terms are still n, because we are starting from 0. Okay, we are starting from 0 here. So the answer is 1 minus 1 upon 2 raised to power log n 1 minus 1 by 2. Okay, so it's basically 1 plus n. And if you try to solve, because it's base 2, if you try to solve this again, if you try to solve this whole thing again, it will be 0. This whole thing will be 0. Because we are saying that 1 raised to power log 2n. And this is very small, so this will be 1 minus 0 upon 0.5, which is 1 by 2. Okay, so it's basically 1 plus n. We can write it as order of n. Okay. So now let's look at this question again with master theorem. What is the value of Fn? It's n. A, which is 1, B, which is 2. Right? So what's n log B A? It's n log 2, 1, which is basically this term is 0. Log 1 is 0. Okay, so it's n raised to power 0, which is basically 1. So which one is greater? Fn. Fn is basically omega of this is the condition which is satisfied. This is case 2. If you remember, this is case 2. So in this case 2, the answer is theta of Fn, which is theta of n. is the same thing we reach till here. So in substitution method, the method is long, but basically what we try to do, we try to replace it. We try to replace each term, and we will go back, we will try to iterate it that as many times as we reach to the base condition. So we need to try to reach to base condition in our case, and we are good. So for a mathematical term, this is very complex example. This is quite complex. If we goes in the power of n, here the power of n is 1/2. Okay, if this is the case, it's a quite complex example, you can see. Okay, right. So I will try to solve this question with recursive tree method also, but right now let's look at this example. This is quite complex example. So let's see that we will try to reach to this base case. Okay, so Tn is given that n raised to power 1/2, T n raised to power 1/2 plus n. So we have to replace root n or n raised to power 1/2 here again to solve this term. Okay, so it will be n raised to power 1/2. If you try to replace this thing here, it will be n raised to power 1/2 multiplied by 1/2. Right? You are replacing n with 1/2. It's already 1/2, so power gets multiplied. Right? And here it's t n raised to power 1/2 square again here, and plus n raised to power 1/2 here, plus n is outside again. Right? So we need to solve this term, this whole term we need to solve. If you don't know like how we reach to this term, we simply replaced n root n with, so here the power is n by 1/2, we replaced n with 1/2 again. So it's n 1/2, 1/2, right? So it's n 1/2 square, right? Similarly, this is we get here, and here only we replaced n with n raised to power 1/2. Okay. So if we multiply this with this, we get n again. And we multiply this with this, we get n raised to power 3/2 square. Okay. Because in case of n multiplication, like if you multiply n 1/2 with n 2 square, the power will add. Okay, power will get added here. 1/2 plus 1/2 square, which is equal to 3/2 square. Okay. Here it's n 1/2 square plus, if you multiply this with this will become n, plus this was already there, n. So now we have to replace n with n raised to power 1/2 square. Okay, we have to replace n with n raised to power 1/2 square, right? Here in this equation, if we replace n with n upon 1/2 square, it will go like this, n raised to power 3/2 square. Let me solve one more term, then I will directly go back to the base condition, and I will tell you how many times we will iterate it. We'll iterate it k number of times, and what is the value of k. Okay, so let's find out this term. Okay, we have n plus n already. What is the value of this we will get? It is n raised to power 1/2 cube. Right? Remember this function. Here we are replacing n. Instead of n, we are replacing n with n upon 1 raised to power 2 square. Right? So this will become like this. And the power will n upon 1/2 cube. Right? T. Okay. So what is this term? 1/2 square. Okay. So now let's solve this problem next step. Okay. So now if you multiply with this, these two will get added. Okay, these two will get added. So now let's do this first. 3 upon n square multiply by n 1 by 2 square. Right, let's add the power 3 by 2 square plus 1 by 2 square. This will become 2 square and 4 there, right? So these two will cancel and it's n is for 1, which is n. Right, this will again become one more n. Again, it will become one more n. And if you multiply these two, the power will get added and it's n upon 7 divided by 2 cube, right? I hope we reach till here and you understand it. I hope you understand till now, right? So let's normalize this one. 2 cube, okay, the power is 3 here. P 1 upon 2 raised to power 3, the power is 3 here, and we have reached till n, right? So whatever power you reach here, the same number of n you will get here, the same number of n you will get here. So if we iterated it k number of times, right, to reach the base condition. Okay. Let me normalize more. It's n instead of 7, we can write it like 2 raised to power 3 minus 1. Okay, here 3 also can be written as 2 raised to power 2 minus 1. So here we can write it 2 raised to power 3 minus 1, 2 raised to power 3. Okay, this whole thing is in power of n. 1 upon 2 raised to power 3 plus 3n. So if we iterate it k number of times, it will become 2 raised to power k minus 1 upon 2 raised to power k. Okay, t 1 upon 2 raised to power k plus 3 plus k n plus kn. Right? Now, what is the value of k? Suppose this is this t 1 upon 2 raised to power k is, if you check the base condition, it says this n is 2. We are saying that this is we iterated this k number of times and this has become t2. So 1 upon 2 raised to power k becomes 2, right? Using this, we can calculate the value of k. K value will become k. If we apply log both sides and do all the calculations, it will become, we found out that, sorry, we are saying that n raised to power 1 upon 2 raised to power k is actually 2. If we again apply the log both sides and do all the calculation, k will become log n. I have already done this kind of calculation. Okay, where if you are seeing that in the iteration, we are basically either doing the I equal to I square. You can check that example. While I is less than n, we are doing I equal to I square. You can check that example in asymptotic notation again. We have reached to this condition. Or we were doing something like n equal to n by not 2. We were doing something like n upon root 2. If we root n, right? Like if we are increasing the power, or we are dividing it by 1 by 2, or we are doing the power like something like n equal to n by 2 at each iteration, we have to iterate log n time. right? So the k value will become log n, and here it's become like n raised to power 2 raised to power log n minus 1, 2 raised to power log n. It's become 2 multiplied by 2 plus n into log n, because this term was k multiplied by n, right? So n multiplied by k can be written like this also. So it's n log n. And this whole term will become n only. Let me show this for you. 2 raised to power log n divided by 2 raised to power log n minus 1 by 2 raised to power log n. Okay, this will become 1. So it will become, this term is getting as it is. So yeah, I can write it like p. This is p. N raised to power, here we can write this whole term as 1 minus 1 upon 2 log n. Okay. Okay, so this whole term will become 1 upon 2 raised to power log n. This is very small, very small. So you can write it as n, 1 minus very negligible 0. Okay, so it will become n. N plus p, and p is equal to n log n. So if it's n plus n log n, we will consider the bigger term. So it's n log n. This is the answer. Okay, so this is a substitution method. If you didn't understand the previous example, you can go through it again and you can try to iterate it like this. Okay. The main step is how many times should we iterate it? How many times should we iterate it? If we reach to this generic, the main thing is to understand the generic form. If we understand this generic form, this is the most important part. If we reach till this generic form, we can say that the k is the answer. Like how we need to identify how many times we iterate it. So we iterated it k number of times, and what is the value of k? We are saying that n upon n raised to power 1 upon 2 raised to power k time we have iterated, which is equal to 2. So if you apply log both sides and try to solve this again, the k value will become log n. It's very easy. Like if we say that it's 2 raised to power k equal to 1, okay, or 2, doesn't matter. Let's apply log both sides. Okay, so once you apply log, it will become 2 raised to power k log n, 2, it's 2 equal to, if we apply log 2 base 2 here, it becomes 1, and log n equal to 2 raised to power k, and if we have to apply log again, so it will become log n. Okay, so till substitution method we are done, right? So there are some more problems. You can go through that because there may be some substitution in recurrence relation. Which are more complex compared to this one, which could be which could lead to Apgp problem. AP and GP both are there. Right now you have seen only arithmetic progression. In the previous example, if you see previous example here, this is the arithmetic progression. So you may lead to arithmetic plus geometric progression also, right? You just have to do the substitution. So once you reach till arithmetic plus geometric progression, you can check on internet like how to solve arithmetic plus geometric progression. Okay, so this is more covered in the engineering mathematics. Okay, so I've given you very basic understanding of substitution, recurrence tree, as well as this problem, this solution, master theorem solution. So let's have the same problem in recurrence tree. How can we calculate the time complexity using recurrence tree, right? So some simpler problem, something like this. Okay, so it's Tn equal to Tn by 2 plus n, right? If something is written like this, what you can do, you can build a tree. Okay, and you have to calculate like what is the depth of this tree, right? So till we reach the base condition, we need to create the tree. Okay, so let's have a tree. It's saying that each time we split it, the input become n by 2. Okay, the input become n by 2, but the effort is n. Effort is n on the first level. So for example, n input is here. Okay, if n is the input or effort applied here in the initial node. To solve the problem, n is the effort, right? But in the next level, the effort apply is n by 2, right? We have reduced the size to n by 2, and that is the effort. Right now, input is n, effort is n. In next level, n is replaced by n by 2, the effort is n by 2. Okay. In the next level, effort is n by 4. Right. In the next level, effort is n by, like this is 2 square, effort is 2 cube. It will go till it become 1. Okay, and how many times we actually done the effort? How many times we have gone through this tree? Log n time. Okay, so if you add this n upon n by 2 plus n by 2 square plus n by 2 cube plus this n upon 2 raised to power log n times you have iterated it. Like you know that this condition that n upon 2 raised to power k is equal to 1. So what is the value of k? Right? If we iterate this tree n number of times, k number of times, k times we iterated it, the value of k would be find out like this. Right? Okay. So you have done this effort calculation at each level. Right now there is only one node. Okay, there is only one node here. We could have created multiple nodes, but we have seen only one recurrence relation again. It's not 2, it's not 3, it's there are not multiple recurrence relations. So I will solve one more recurrence relation example, but right now we are having only single recurrence relation here, single. Okay, that's why only single node at the next level. At the next level, we'll have one more node, single node, and the effort is n by 2, n by 2 square, n by 2 cube. If you add all these things, taking n common 1 upon 1 by, so 1 by 2 0, 1 by 2 1, plus 1 by 2 square, plus 1 by 2 3, till 1 upon 2 by log n, right? Something like this. If you calculate this one again, it will lead to 1. We have calculated already, right? Here in the previous example, we have already seen that this will lead to this whole GP will lead to this one. Okay, which is 1. So here the answer is n. Okay, so how to solve recurrence relation using this recurrence tree? If you are given something like this, t n by 2 plus n, something like this, right? So you can write it like this, t n by 2 plus t n by 2 plus n, right? So instead of single recurrence, you have 2 recurrence. So you create 2 nodes. Here, the effort is n at the root node. Now you have n by 2 input and n by 2 input, and the effort is n. N means n by 2 here, n by 2 here, and the sum is n again. And again you create 4. So it's n by 4, n by 4, n by 4, n by 4. The whole sum again will become n. So right now you will iterate this again n upon 2 raised to power k number of times till it become to the base condition. Okay, and effort at each node, even at the leaf node, even at the leaf level, last level, it is n. And once you sum all these, the number of levels are log n, right? Similar to the previous problem, you have seen that number of levels were log n. Here also number of levels are log n, and effort at each level is equal to n. Okay, so there are log n levels. So the answer is n log n. So now let's do it using master theorem. Here Fn is n, and n log Ba is equal to n log 2, which is n also. So this is the third case of master theorem. Let's go back to the master theorem. Third case of master theorem says that if these two are equal, Fn and n to the power log Ba is equal, the answer is basically Fn log n or n log Ba log n. Okay, so it's n log n. Okay, so master theorem matches with recurrence tree method also. So in recurrence tree method, you basically identify the recurrence terms, like here this is one term, this is second term, and the total effort at the base level is n. Okay, this n is equivalent to this one. So once you replace it with n by 2, it will become T n by 2 square plus T n by 2 square plus n by 2, right? So that's why at this level, at the second level, okay, at the second level, you have seen that we have two recurrence relation. One is this one is this one. Okay, two recurrence relation equivalent to two nodes. Okay, and the effort for n by 2 is n by 2. Effort for n by 2 is n by 2. Effort for n by 2 is n by 2. That sum is n. I hope this clarifies your doubt. So thank you all. We will see some more interesting concepts. Now we will be moving to, let me give you the brief about the next one, to the divide and conquer, DNC. Okay, divide and conquer concept. So we will start from this binary search. We will also cover merge sort. So these are divide and conquer algorithm: merge sort, quick sort. Okay. So these are main divide and conquer problem. We will solve these problems tomorrow. Then we will move to this greedy algos. Thank you all for joining.